NASA's James Webb Space Telescope has hardly opened its eyes and the universe is new. It's clear that Webb represents the best of NASA 40 light-years away. Nestled around a dim red dwarf star lies one of the most intriguing planetary systems ever discovered, TRAPPIST-1. Unlike our own solar system, where planets spread across vast distances, TRAPPIST-1's 7 Earth-sized worlds are packed into orbits so compact that they could all fit within Mercury's path around the Sun. At first glance, such proximity to their host star might seem hostile to life. Yet astronomers believe that some of these planets could harbor conditions suitable for habitability. But wait, did James Webb find an atmosphere near TRAPPIST-1? Well, let's answer this, and much more today. The TRAPPIST-1 system comprises of a compact arrangement of Earth-sized worlds, orbiting an ultra-cool red dwarf. At the heart of this system is TRAPPIST-1, a star with only about 12% of the Sun's radius and a mere 9% of its mass, making it barely larger than Jupiter. Its surface temperature hovers around 227 degrees Celsius or 440 degrees Fahrenheit, classifying it as a low-luminosity, low-energy output star. Unlike the Sun, which radiates high levels of visible and ultraviolet light, TRAPPIST-1 primarily emits infrared radiation, which has profound implications for the planetary climates and atmospheres of its orbiting worlds. What makes the TRAPPIST-1 system particularly fascinating is its unique planetary architecture. All 7 of its known exoplanets are Earth-sized with diameters ranging between 0.76 and 1.13 times that of Earth. Despite their physical similarities, these worlds are packed into orbits so tight that the entire system could fit well within Mercury orbit around the Sun. But despite this, they may harbor life. Yes, life may indeed have finally found a way. The way these planets are packed allows for strong gravitational interactions, leading to orbital resonances. This is when planets tug on one another in predictable ways, affecting their orbits and rotation. These interactions combined with transit timing variations, which are slight changes in the timing of a planet's transit across its star caused by gravitational interactions with other nearby planets, enable scientists to determine the masses and densities of the planets. With remarkable precision, data suggests that these planets are mostly rocky, with little to no hydrogen-dominated atmospheres, making them prime candidates for studies on potential habitability among the 7 planets. TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g reside within the system's habitable zone, the so-called Goldilocks zone, where conditions might allow for liquid water to exist on the surface. However, the likelihood of surface water also depends on atmospheric composition, greenhouse effects, and stellar radiation. However, TRAPPIST-1's extreme age, estimated at around 7.6 billion years, makes it older than our solar system. This has raised intriguing possibilities. With such an extended timescale, any potential biological processes could have had far longer to develop than those on Earth. Yet this longevity also presents challenges, as older red dwarfs can exhibit prolonged stellar activity, including intense stellar flares and ionizing radiation, which might strip away planetary atmospheres or alter their chemical compositions. The TRAPPIST-1 planets, due to their close orbits, are likely tidally locked, meaning one hemisphere permanently faces the star while the other remains in perpetual darkness. This could create extreme climate zones with a torching day side and a frigid night side, unless atmospheric circulation helps distribute heat more evenly. Studies suggest that certain atmospheric conditions, particularly thick carbon dioxide-rich atmospheres, could mitigate these extremes, potentially making some planets more Earth-like in their climate stability. So could these planets host life? Well, let's get some context first. The role of atmospheres in habitability. The habitability of the TRAPPIST-1 planets is heavily influenced by the presence and composition of their atmospheres, which play a crucial role in determining surface conditions, temperature regulation, and the potential for liquid water. However, their close proximity to the ultracool red dwarf poses significant challenges for atmospheric retention. Intense stellar radiation and strong stellar winds could strip away lighter elements, particularly hydrogen and helium, leaving behind only dense secondary atmospheres. If any at all among the 7 planets, TRAPPIST-1e stands out as the most promising candidate for habitability, as it may have retained a secondary atmosphere rich in heavier molecules like carbon dioxide, nitrogen, and possibly even water vapor. If this atmosphere is dense enough to regulate heat distribution and protect against stellar activity, TRAPPIST-1e could host conditions suitable for life understanding. These atmospheres requires advanced observational techniques, with astronomers employing cutting-edge space telescopes to probe the chemical compositions of these distant worlds. The Hubble Space Telescope was instrumental in early studies of the TRAPPIST-1 system, using transmission spectroscopy to analyze steroid passing through planetary atmospheres. These observations ruled out thick hydrogen-dominated atmospheres for TRAPPIST-1b and TRAPPIST-1c, suggesting that if they have atmospheres at all, they are likely composed of heavier gases, rather than being Neptunes with extensive hydrogen envelopes. The James Webb Space Telescope is now revolutionizing our understanding of the TRAPPIST-1 system by providing detailed infrared observations by detecting specific absorption features in starlight as it filters through planetary atmospheres. JWS can identify key gases such as water vapor, carbon dioxide, and oxygen. Initial thermal emission studies have already revealed that some planets like TRAPPIST-1b likely lack substantial atmospheres, with secondary eclipse observations confirming it is a barren airless rock. As JWST continues to study the system, upcoming data will shed light on whether any of the other planets, particularly TRAPPIST-1e, retain atmospheres capable of supporting liquid water. If some of these planets have indeed managed to retain substantial atmospheres despite the host star's high-energy radiation, it would significantly expand the potential for life-bearing worlds around low-mass stars. On the other hand, if most or all of these planets have been stripped of their atmospheres, it would raise serious concerns about the habitability of similar planetary systems throughout the galaxy. But wait, there's more challenges of red dwarf stars for habitability. Red dwarfs are the most common stars in the universe, offering an abundance of planetary systems, yet their harsh stellar environments pose serious challenges for life as we know it. In their early evolutionary stages, red dwarfs like TRAPPIST-1 undergo an extended pre-main sequence phase that can last for approximately 100 million years, during which they are significantly more luminous than in their later stable phase. This prolonged period of high-energy radiation results in extreme ultraviolet and X-ray exposure for any orbiting planets, particularly those in the habitable zone, making it difficult for atmospheres to survive, one of the most severe threats to planetary atmospheres. In red dwarf systems is hydrodynamic escape, a process driven by intense stellar radiation. As a young red dwarf bombards its planets with high-energy photons, atmospheric particles heat up, expand, and are gradually stripped away into space. This effect is particularly devastating for lighter gases such as hydrogen and helium, but it can also lead to the depletion of heavier molecules like carbon dioxide and water vapor over extended periods, even if a planet initially formed with a thick, life-supporting atmosphere. Sustained radiation exposure could erode it down to a barren, airless surface, unless a significant replenishment mechanism, such as volcanic outgassing or cometary impacts, counteracts these losses, adding to the instability. Red dwarfs are notorious for their frequent and violent stellar flares, which can release bursts of high-energy radiation and charged particles. These flares, sometimes thousands of times more powerful than those from the sun, have the potential to ionize upper atmospheres and drive away critical atmospheric components. Through stellar wind-stripping planets that lack strong magnetic fields are especially vulnerable, as they have no protective barrier to deflect these charged particles. If a planet like TRAPPIST-1e orbits within the habitable zone, but lacks a sufficient magnetosphere, its atmosphere may be continuously eroded by these stellar winds, further diminishing its potential for habitability. Despite these challenges, some scientists argue that certain planetary conditions could mitigate these effects. A planet with a sufficiently massive atmosphere, rich in heavier gases like nitrogen or carbon dioxide, might be able to resist complete atmospheric loss. Likewise, a strong planetary magnetic field similar to Earth's could shield against the worst effects of stellar radiation. However, given the compact orbits of the TRAPPIST-1 planets, where all 7 worlds are packed within a distance smaller than Mercury's orbit around the Sun, sustaining such protective conditions would require exceptional geological or atmospheric resilience. So what can we expect in this situation? Why TRAPPIST-1e might retain an atmosphere despite the extreme stellar conditions imposed by its red dwarf host TRAPPIST-1, E may have retained an atmosphere. One of the key reasons for this is the possibility that the planet initially formed with a thick primordial hydrogen atmosphere, which over billions of years may have been gradually stripped away due to stellar radiation. As this early hydrogen envelope dissipated, TRAPPIST-1e likely developed a secondary atmosphere through volcanic outgassing, a process in which internal geological activity released gases such as carbon dioxide and water vapor from its interior. This transition is crucial because a secondary atmosphere composed of heavier molecules is more resistant to complete erosion compared to the light hydrogen atmospheres that many exoplanets lose in their early stages. Another critical factor contributing to TRAPPIST-1's potential atmospheric retention is its distance from the host star. While still in a compact orbit, TRAPPIST-1e is farther from the intense radiation zone compared to inner planets like TRAPPIST-1b. TRAPPIST-1b, located closest to the star, has almost certainly lost its atmosphere due to the relentless bombardment of stellar wind X-rays and ultraviolet radiation. The reduced exposure to X radiation at TRAPPIST-1e's orbit may have slowed the rate of atmospheric loss, allowing it to retain a more substantial atmosphere over time. Additionally, if TRAPPIST-1e possesses a strong magnetic field, it could provide an additional layer of protection against atmospheric stripping. By deflecting charged particles from the stellar wind, outgassing from early magma oceans on TRAPPIST-1e could have played a fundamental role in replenishing its atmosphere with greenhouse gases such as carbon dioxide, which would help regulate surface temperatures and maintain liquid water if conditions are right, unlike gas giant planets which retain hydrogen and helium. Rocky exoplanets like TRAPPIST-1i depend on internal geological activity to sustain their atmospheres over geological timescales. If volcanic activity has continued over billions of years, it could have provided an ongoing source of carbon dioxide, strengthening the planet's atmospheric stability and making it more resistant to gradual erosion. But to see is to believe. For that, we must wait. If TRAPPIST-1e is found to have a significant atmosphere, it would suggest that Earth-sized planets orbiting red dwarfs may be more resilient to harsh stellar environments than previously believed. Conversely, if JWST detects little or no atmosphere, it would reinforce concerns that red dwarf planets may generally be inhospitable for life, for the sake of argument. Let's assume the first possibility is true. Can we then finally make first contact with an alien life form? And even more importantly, why haven't we done so already? Where is everybody? This question is not new. In fact, this is precisely what physicist Enrio Ferri pondered in the 1950s with billions of Earth-like exoplanets scattered across the galaxy. The sheer probability suggests that intelligent life should have emerged multiple times yet. Despite decades of radio signals, space probes, and SETI, or search for extraterrestrial intelligence efforts, we have found nothing but silence. Moreover, the Drake equation, developed by astronomer Frank Drake in 1961, attempts to estimate the number of active communicative extraterrestrial civilizations in the Milky Way. The equation factors in variables such as the rate of star formation, the fraction of planets capable of supporting life, and the likelihood of technological advancement, while the equation provides a framework for estimating the probability of extraterrestrial intelligence. It does not address why we have yet to detect any signals or evidence of alien civilizations. So how come there is only silence? Some argue that intelligent life may be exceedingly rare, with civilizations either self-destructing before achieving interstellar capabilities or existing at such vast distances that communication is impractical. Others propose a more unsettling possibility that TEE civilizations are intentionally silent because broadcasting their existence could lead to catastrophic consequences. The dark forest hypothesis, introduced by science fiction writer L. Tixon in his 2008 novel The Dark Forest, presents a chilling perspective on why the cosmos appears so eerily quiet. The hypothesis suggests that all civilizations in the universe are like hunters in a dark forest, each moving cautiously in recognition. Future space missions. may identify Earth-like planets faster and refine methods for detecting extraterrestrial life. Despite the immense distances and challenges associated with interstellar exploration, the progress in space science brings hope that humanity will one day bridge the cosmic divide with each new discovery. Whether a magnetized exoplanet, a habitable world, or an unidentified signal from deep space, we move closer to answering the profound question, are we alone in the universe? The future of space exploration is filled with promise and with continued innovation, collaboration, and curiosity. The next great discovery may be just beyond the horizon. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.